Hello everyone. So am I audible? Okay, let's assume that I am audible. So, okay, thank you. So welcome to this live interactive session for week 1 of the course Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am the host for this tutorial session. So the objective of the course is to actually provide a general overview of the subject and to develop the basic concepts and to develop the skills for geometric interpretation and linking the geographical disposition of geological structures, and also to develop a strong sense of scale dependence of geological processes both in time and space, to develop an understanding of the different deformation processes and mechanisms that govern the formation of geological structures, to connect structural geology with other domains of earth sciences such as petrology, geophysics, hydrogeology, ore geology, mining engineering, etc. And of course, to provide an understanding of lithostructural mapping from outcrop to regional scale that are important for mining and exploration industries. So now coming to the live sessions, actually, what are the usefulness of this live interactive session is actually to clearing doubts on the course materials and discussing conceptual and numerical problems on structural geology that will help in solving the weekly course assignments, and to discuss multiple choice based and numerical questions relevant for national level competitive examinations in geological sciences such as GATE, NATE or JAM, CUET, CUPT, etc. And of course, to provide some glimpses of recent research directions in structural geology and tectonics and discuss some of the future opportunities in research and academia. So I myself pursuing PhD in structural geology, and so this curriculum of live session is one of my teaching requirements that I have to fulfill, and it is also a great opportunity for me to actually interact with the person or the people who are joining the course online through NPTEL. I think this is a very great platform to not only build you know the basic understanding on the subject, and also actually to build a platform over which we can discuss and exchange ideas on structural geology and these kind of things. So this is the course outline. So from the very first week, we should cover the basic concepts of structural geology, and then in the second week we have the structural elements, measurements and stereographic projections. Then comes the concept of strain, the concept of stress, rheology of materials and rocks, deformation mechanisms of materials and rocks, foliations and lineation, ductile deformation that includes the mechanism of folding and superposed deformation, and then the ductile deformation also comes in the boutinage and related structures. Then comes the brittle deformation that includes fractures, joints and faults, and then comes the concept of ductile shear zones. And finally, by integrating all of the above relations, all of the above topics, we build on the concept of lithostructural mapping, and that can be applied to a regional scale, and from which we can also understand how a regional tectonic deformation has taken place and different uh, localization events of deformation has taken place. Now, the live interactive sessions will be hosted from this date onwards on each Saturday of each week, and it lasts for about 12 weeks, the entire duration of the course. So the purpose of this live interactive session, as I've told before, is that actually to discuss the overall things that you guys are learning in that particular week. Say for example, this is week 1, so we will talk about the materials that you learned in the week 1 lectures, and then for the upcoming series we will follow on the different weekly lecture contents like week 1, week 2, and that will progress through different problem solving sessions we will discuss. And if you have any doubt on certain materials on the weekly content of the lectures, you can also share me by, you can also email me, and we can also discuss here in this live session. So the time is fixed. It's so we will start from 5 p.m. onwards. So it's 25th July 2026. So after that, on each Saturday from 5 p.m. to 7 p.m. we will join in this live session, and if you have any doubts we can discuss. And this is the link to join the meeting, right? So about today's live session, it's more on the content of the week 1. So in week 1, what we have learned in week 1 is the importance of this subject, different aspects of structural geology, the importance of scale of observation, homogeneity and heterogeneity of geological structures, interpretation of information via geometric models, kinematic models, mechanical models, numerical models, and analytical methods. So these was the overall content of week 1. And for topics of today's discussion will be mostly on interaction about the week 1 course content and answering doubts if you have any doubts, solving some problems. So we will solve some of the problems like MCQ problems that are more close to the actual assignments that you will get. So through solving with me, through this interactive discussion, we will actually know how to tackle questions that can come in the assignments, and these assignment questions are also related or oriented in such a ways that these are the standard patterns in which national level examination questions will also come. So by solving these problems, you can also have a practice on solving MCQ questions that can also include numerical answer questions, and that will actually strengthen your understanding of the subject, right? Okay, so I have prepared 10 basic questions since this is the week 1. So each week we will try to solve mostly 10 to 15 questions. These will be MCQ type questions. So I will introduce one question. So this is how it will go. Like, I will introduce you one question. This will be displayed on the screen, and I will give some time to you so that you can solve the questions on your own, and then we can discuss about the answers and how we are interpreting these questions, and then we will follow on to the next question. So this is how it will be done. So for the week 1, I have 10 questions here. I will display one after another. So we will solve one question and then move on to another question. So that's how it will happen. So for each question, I may give you 5 to 10 minutes. Although these are very basic questions, you probably don't need that much time. But going onwards to the next week's content or the other, so there might be some numerical problems that you have to work on using pen and paper or even using a calculator. That may take some time. So in through like this, we will actually uh, talk how to deal with numerical problems, especially what are the formulae that I'm using to solve these problems, and we can actually go beyond what we already learned in the weekly content of the lectures, and then we can also introduce some more advanced stuff. So that's up to the next week. So first, let us start with a very basic question. Question number 1, which says that which of the following options best explains why structural geology is important for understanding earth processes? And the option A is it only studies the mineral composition of rocks. Option B, it helps decipher the deformation history and tectonic evolution of a region. Option C, it exclusively deals with fossil record dating. And option D, it is unrelated to the natural resource exploration. So it is very easy as you think that. So which one will be the correct option? It's fairly easy. You can answer this. So any guess from anyone? Okay, so I think it is very easy. So structural geology actually helps decipher the deformation history and tectonic evolution of a region. So structural geology is basically the study of different kind of structures that we generally see in rocks, right? So, and why we say that uh, some structures are deformed and some structures are not, it is it this concept basically comes from understanding the uh, you know uh, the the principles of uniformitarianism that tells us that whatever that has happened in the past are also happening in the present, and so like observing the present can actually decode the past. So we have seen the deformation of metals, we have seen the deformation of other materials that are commonly present on our earth, and from that observation we can actually relate also, okay, so if a metal deforms like this and produces some kind of structure, and we also see that that same kind of structure is also present in some rocks, that means that these rocks, they must have deformed uh, before whatever there was present. So it's like it's a very ancient thing. That means the deformation has taken in the past, and that's how people started observing rocks as materials rather than just rocks as rocks. So rock, like any other material, say for example metals or alloys or ceramics or these kind of things, rock do also behave like any other material. So from a material perspective, when people are try to understand how metals or ceramics behave, they also started looking for how rocks would behave if they're subjected to the same kind of condition. And that's how, you know, going from understanding how the deformation has taken place, one has to understand how the geometry is important, because some irregular geometry like fold, or some regular pattern geometry like fault, or any other kind of structures whatever there may be, these things are typical geometry that are produced due to the response of external perturbations. So external perturbation of course means forces that are acting on nature, acting in nature. And using this tool of observation, particularly the observation of geometry of different structures, we tend to decipher how the deformation has taken place. That's all about structural geology. It's first understanding the geometry of anything and then move on to the interpretation of that geometry, right? So that's it. So it's a very basic question about structural geology. Okay, so in a similar manner, as just I have already mentioned, is that structural geology is the study of structures, and to study structures we need to first observe the geometry, right? And upon observing the geometry we then try to infer what is actually happening. So on that note, the second question actually says is that structural geology integrates geometric, kinematic, and mechanical aspects. Okay, so which of the following pairs correctly matches an aspect with its focus? Option A: geometric describes shape and orientation. Kinematic describes the forces causing deformation. Kinematic describes the movement and path of particles during deformation. Mechanical describes the forces and stresses responsible for it. Option C, mechanical describes only the final shape of structure, geometric describes the forces involved. And option D, geometric and kinematic aspects are identical with no distinction between them. Right, so this is apparently easy, but it's a trick question, so you have to think thoroughly. Again, if I repeat the options, so the option A describes, geometric describes shape and orientation, kinematic describes the forces causing deformation. Option B, kinematic describes the movement and path of particles during deformation, mechanical describes the forces and stresses responsible for it. Mechanical describes only the final shape of the structures, geometric describes the forces involved. And option D, geometric and kinematic aspects are identical with no distinction between them. So think what could be the final answer. I give you some time and I need one answer or one response because it is an interactive session. So I expect that I should get an answer from you. And okay, so it may be wrong, it may be right, doesn't matter. We will discuss anyhow. Okay, so let's give your time and then I can ask you later. Okay, so take time and go for an answer. Okay, Pragya says that the option B is the correct answer, and let's see if any answer comes. Any other answers are coming. So, any other answer? Anyone? Okay, Alicia is also saying B. Yeah, so the correct answer, of course, is B. So, geometric aspect is basically shape and structure, and it is essentially the final shape, right? Kinematic aspect is essentially to deal with the sense of motion, or in other words, understanding the flow of particles, right? And mechanical aspect is actually the forces acting, and which is also known as the dynamics, right? Okay, so I have one question. So instead of putting some comment, you can try unmuting yourself and just answer the question. It's rather it will be good because we can interact then. So the question goes like this. So imagine a situation where there are no plate tectonics operating, right? Because if I say that the tectonics is operating, then of course the tectonic forces like the collisional boundaries or the transform faults or the mid-oceanic ridges or the convection current inside inside the mantle, these kind of things will come. So I'm not going into that deep. I'm just asking you a question like this. Say for example, consider situation where there are no active tectonic processes going on this planet, right? Say for example, whatever the structures are were there, like the mountains, they have been formed, like the mid-oceanic ridges, they have been separated and all the plates have just settled down and the subduction process is going on no more. So in that aspect, I mean, in that case, do you think there will be left any such force that can drive the deformation on the earth surface? So if you do not understand my question, you can ask me. I can also repeat one more, repeat once more. So what I am trying to convey is that you have to imagine a situation where there is no active tectonics on the planet, right? Whatever there has been, it's all done, and now the planet is sitting like there is nothing going inside, so there are no tectonic forces that could drag plates and, you know, like make a collision, generate tectonic stresses and the geodynamic processes and all these things. I'm considering a situation where there are no tectonic forces. So in absence of all the tectonic forces that are currently going on in the earth, in the absence of all these forces, will there remain any force on the surface, I mean, that can, you know, drive any sort of deformation process on earth? Any answer? Please, can you unmute yourself? So because actually I'm sharing the screen, so I don't often get to see the comments. That's why I'm saying. Every time I have to see the comment, I have to switch off the screen share, and then I have to go to the main Google Meet page, and then I have to look for it.
Sir, maybe gravitational force.
Exactly, you're right. Gravity. So even there are no operational tectonic forces, gravity could do the work. Actually, gravity is actually one of the most important forces that drives the deformation on Earth. Whatever you're actually seeing, from starting from the mountain building and anything. So gravity is one of the most important aspects of the deformation, because even for tectonic processes that are currently operational, say for example glacier melting, or subduction, or transform from a transform boundary, or a mid-oceanic ridge, the magma is coming out on the ocean floor, it is being stored there, depositing. So every time there are some tectonic processes, whether it's a subduction zone, or there is a glacial melting, or some magma is concentrating in something like a batholith or so, these actually uh, you know hampered the local mass distribution inside the crust. And if there are imbalances in mass distribution, that means there are imbalances in the density inside the lithosphere, that would contribute to the isostasy on the particular, in that particular location. Like, and then for isostasy, what will happen? Isostasy is one of the important part that drives that relates whatever that is going inside the lithosphere, that is being connected to the earth surface, as a response to the isostasy. So isostasy is very much important, that not only drives uh, you know the distribution of mass inside the earth, but it also one of the important processes that connects whatever that is going on inside the earth in the lithosphere to its manifestation on the surface. So why isostasy is very important? So I can tell you a stories like that. People came to understand isostasy about from studying the glaciers. Right. So due to the movement or the deglaciation or the melting of the glaciers, some landforms started to uplift. So there is an upliftment that was recorded, and the melting of the glacier. The scientists correlated the upliftment with the melting of the glacier, and they found that the rate of upliftment is actually equal to the rate of deglaciation. And from that they actually inferred is that since the mass that was sitting at the top of the crust, it's a heavy glacier, the continental ice sheet kind of structure. Now since it is melting away, the mass is being moving away from that particular location, and for that, the lithosphere basically it's having a flexural uh, movement, so it's flexing upwards, and that's how the upliftment is happening. So that kind of deformation, it's a purely ductile deformation, right? I mean there may be some little deformation or faulting involved, but in majority it's a ductile deformation, and it happened only because of gravity. So gravity is one of the fundamental forces that we do consider when we are studying structures. And even the deglaciation and the upliftment is also a very long-term process. In a very short-term process that we can also, visualize in our human lifespan, is landslide. Right? Landslide, very importantly, it is majorly driven by gravity. Of course, there are role of tectonic processes that's why landslide doesn't occur everywhere. The landslides are occurring in some parts of the orogeny or the mountains where the upliftment rate is high. So of course you can correlate landslide somehow with the tectonic processes, but in reality the dominating or the major contribution comes actually from gravity itself, because gravity is pulling all the material that is being, you know, sliding over the landslide fault surface, right? So if there are even no forces present on earth, inside earth, the tectonic process has been stopped, gravity will continue to contribute to deformation on the earth surface, right? It's everything that will only occur on the, I mean, above the soil layer, and nothing will be going on inside the lithosphere. Okay. Now coming to the third question. The concept of scale of observation in structural geology emphasizes that, option A, all structures behave identically regardless of scale. Option B, microscopic scale observations can always be extrapolated without modification to regional scale. Option C, the style and mechanism of deformation can differ depending on whether the scale of study is microscopic, mesoscopic, or regional. And option D, scale of observation is relevant only to seismology and not to structural geology. Now, this can be potentially a multiple select question. Like there can be more than one questions, more than one options can be correct in this case. So I need you to think thoroughly and answer which of the options could be the correct answer.
B and C.
B and C. Okay. Any other answers? Okay, just I will let you think another 5 minutes, because yeah, I think one of the options is correct, but then I might be disagreeing with another option as well. I think another option is correct instead of the other one that you have told. Okay, so yeah, think about that. Okay, so Alicia is saying that only option C is correct. Okay, so one thing's for sure, I can say that if option C is correct, which is true, so if option C is correct, then option B will not be correct, right? Then you think about that. Why I'm saying that if option C is correct, then B is not correct. And if B is correct, then option C is not correct. Why these are two contradictory to each other? Okay, so one thing is that um, this meeting link can potentially expire before 1 hour. So that's why to get an uninterrupted meeting, I have created another link, and I'm pasting that link uh, in the comment box. So if you get a message that this meeting is about to end, they generally do give a warning at 55 minutes. So we will switch on to the other link, and I have pasted the link in the comment box. I mean, in the message box, right? Okay. So now, yes, as I was saying, option B, either option B or option C, only one of them will be correct, right? And I am saying that option C is definitely correct. And since option C is definitely correct, this will be not the correct answer. And then the another correct answer is potentially option A, right? Now, coming to the answer to this question, why option C is correct? Because the style and mechanism of deformation can differ depending on whether the scale of study is microscopic, mesoscopic, or regional, right? Why so? So let me give an example. Like if you observe a fault, say for example, it's a normal fault, right? Say for example, this is a brittle deformation. So in normal fault, they are generally, I mean, in a generally fault structures are bounded by some other fracture networks, damage zones, and things like that. So it is not a simple continuous structure. It involves other complicated subsidiary structures as well. So in a broad scale, if you just observe the thing on a map, so what you will say that there is only one fault. Like, so one fault means one fracture surface. It's like that. It's a single deformation event. So in a map scale, when you're visualizing the fault or the normal fault in a map, you will commonly say that, okay, so this is only just one fault. That means it is only one structures, right? That's it. But then you go to the field and you observe this damage zone. And you immediately come to notice that there are several other. So if this is my damage zone, there will be extremely fragmented rock mass around the fault surface. These are brecciated rocks. This will be known as damage zone. Then there will be the host rock of the hanging wall and host rock of the foot wall, like this. And then the fault surface, even it's not a single surface, but rather you will get some mushy structure made up of cataclysite and all those things. So that is known as the principal slip zone, PSZ. So in a fault, even inside a fault, there are certain segregations of structure. So immediately when you go to the field, you will find out that whatever you have been interpreting in the map is just a line, but it's not simple as a line. You go to the field and you immediately find out it is more than just a line. There are certain layers or different classes of rocks are involved. Different classes of rock, different sections of this part has experienced different types of deformation in the different intensity of deformation. And then you break the rock, you come to the lab and you prepare a thin section and you observe under the microscope, and you will find that even inside the principal slip zone, you can actually find C fabrics and S fabrics like this, which are essentially the signatures of ductile deformation. Some clasps, and then there is a matrix that is being actually showing some flow structures like this. So there is a sense of shear going on like this, and you can immediately say, okay, there is some sense of ductile deformation going on. It's not just pure brittle fracture. So moving from the map where you just draw a simple line, so it's just a fault. Like, so you draw a fault line like this. It's a thrust or normal fault, whatever. And just is a mark the deep and strike like this, and it's done. Right? So in the map, it's just a line. That means it's just a fracture line. That's it, or a fault plane. But immediately, if you go to the field, you find that it's more complicated than a fault plane, because there are different classes of rock, different sections of the rock that has suffered different intensity of deformation. Even though in the field scale, you are also maintaining. So from the map, you say fault is a brittle feature, done. Go to the field, you also see the fault, and you are convinced that, okay, so it is still a brittle deformation feature, done. You collect the rock, you come to the lab and make a thin section, you see that rock under a microscope, then you start thinking, okay, so is it fully brittle? No, I also seeing some ductile signatures there. So that might involve some ductility and not just pure brittle deformation. Now immediately you find that there is another mode of deformation that was only hidden until you find out through the microscope. So it's like scale of observation. As you go down or you go up, you scale up or you scale down, whatever you're doing, you find that multiple processes come to the picture. So the style and mechanism of deformation mechanism, that means whether it is a brittle, whether a deformation, whether it is a ductile deformation, these kind of things. Style means what are the structures that I'm expecting, right? So even in the fault scale, you see that there are breccia, there are cataclysms, there are some shear zones, and the things like that. And you then go to the microscope, you find that, okay, so there are multiple folded structure as well inside the principal slip zone, which is apparently has to be brittle in nature. But then you go inside, you find that there are some small signatures of ductile deformation. Right? So going from regional to mesoscopic to microscopic, things change, mechanisms change, and collectively we get a fault. So in regional scale map, you will say it is a brittle deformation. Even in the field, you will say it is a majorly brittle deformation. But under microscope, the same thing, the rock being the part of the same structure that you have seen in the field, it is telling you another story. It is telling you that it is not purely brittle deformation. There are some signatures of ductility as well. So both style and mechanism can differ depending on whether the scale of study is microscopic, mesoscopic, and or regional. Right? Now, having said that, then why I am saying that microscopic scale observations can always be extrapolated without modification to regional scale, this statement is wrong. Can you present any argument that why I am saying so? If option C is correct, then why option B is not correct? Any answer? Okay, so the thing is, since I've said that structures can appear differently when you are observing at different scale, so of course it is evident that you cannot actually extrapolate whatever you're observing in the micro scale to the regional scale without any kind of modification. Like so, if you had to if you have been presented with something of a like this the fault code, so it's a thin section of or a slide of a ductile shear zone or a principal slip zone from a fault, and you have not been told. So you are observing intense ductile deformation along with fractures, fracture networks, brittle shears, all sorts of things inside that principal slip zone. And then just by looking into that, immediately you have sensed, so this is some kind of shear zone sample, right? And since majority of the structure is ductile in the scale, so you are presuming that entire deformation is ductile. And if you assume that, and if you just extrapolate to that the regional scale, will you be correct to do that? Because in the map scale, it was originally a fault. Only when you went to the structure to actually see that the fault itself is a very complex structure. It doesn't always involve brittle. So in theory or in principle, these are the two extreme ends of deformation that can be achieved, right? Whether the deformation will be ductile or it will be brittle. But in nature, nothing is pure ductile and nothing is purely brittle. It is always a combination of ductility and brittle behavior in some sense. In macroscopic scale, it might be brittle, but in microscopic scale, it can be ductile, or the opposite. In microscopic scale, you see a lot of fractures, but when you go in a mesoscopic scale or in a field scale, you will see it's a fold, right? So the thing is that whatever the deformation is being observed, it represents a scale. So in a field scale, this might be a fault, but that doesn't apply to the microscopic scale when we're observing a slide. And similarly, we just cannot extrapolate whatever we are observing in the slide to the nature. So that is why option B is not correct. But then why option A is correct? Because if you produce fold in microscopic scale, and if you produce a fold in a mesoscopic scale or a field scale, both the things has to undergo viscous deformation or the ductile deformation. So the style of deformation, so all structures behave identically regardless of scale. That means regardless of the scale of observation, whether it is microscopic or mesoscopic or regional scale, whatever the process there must be, if there is a regional fold, that means the region entirely suffered ductile deformation. And if you are trying to replicate the same thing in a microscopic scale, even in that microscopic scale, you have to produce some sort of ductility or viscous deformation, otherwise you will not be able to produce the fold. So the structure behaves identically means you need the same deformation mechanism to produce that structure regardless of the scale, because in microscopic scale you still need viscous deformation to produce a fold. In microscopic scale, macroscopic scale or mesoscopic scale, we will also need to produce viscous deformation. If you are observing fracture networks or faults in microscopic scale, that is the loss of cohesion that creates a fault or a fracture. Similarly, for macroscopic scale, mesoscopic scale, or even regional scale, you need some loss of cohesion to actually produce fractures. That is the simplest thing. So structures behave identically regardless of scale, and the style and mechanism of deformation can differ depending on whether the scale of the study is microscopic, mesoscopic, or regional. So these are the two correct answers to this question. Okay, very good. Then we shall move to the next question, which says that which of the following statements distinguishes homogeneous deformation from heterogeneous deformation? Option A, in homogeneous deformation, originally straight and parallel lines remain straight and parallel throughout the body, which is not generally true for heterogeneous deformation. In heterogeneous deformation, every part of the body deforms by exactly same amount in the same direction. Option C, homogeneous deformation occurs only in brittle rocks, and heterogeneous deformation only occurs in ductile rocks. Whether, or an option D, whether a deformation is homogeneous or heterogeneous depends solely on the color of the rock. I can tell you that there is only one correct answer to this question.
Sir, option A.
Exactly, option A, right? So homogeneous deformation by virtue, because it maintains a homogeneity. That means everywhere you observe in every scale, that is important too. It has to be the same, right? So exact amount of deformation in the same orientation repeated everywhere. That's how parallel lines remains parallel and straight remains straight. So that's why in homogeneous deformation, originally straight and parallel lines, they remain straight and parallel throughout the body, which is not generally true for heterogeneous deformation. Exactly. Okay, so going to question 5. A geometric model in structural geology is best described as one that, option A, predicts the forces and stresses that produce a structure, describes the present day shape, size, and spatial arrangement of a structure without reference to the process that formed it. Option C simulates the velocity field of particles during progressive deformation. Option D relies on numerical simulations to reconstruct the paleostress. And as you know, it has no doubt option A is the correct answer. So, option A. Okay. Question number 6. Which of the following is the best example of applying a kinematic model to a folded rock layer? Measuring the dip and strike of the fold's axial plane, determining the mineral assemblage present in the fold hinge, reconstructing the deep displacement paths and rotation history of particles as the fold develop, and option D, classifying the fold as upright or overturned based on geometry alone. And I can tell you that this also happens to be an MSQ question. That means there has to be two correct answers. Now think carefully what will be the two correct answers. Meenakshi is saying that the option C is correct. Of course, option C is definitely correct, but then which one of the other options will be correct?
Option B and C.
Option B and C. Okay, so determining mineral assemblage present in the fold hinge. Okay, so then let us discuss, like, why do you think that mineral assemblage, understanding the mineral assemblage can help us understand the kinematics of a fold? Yes, of course it can be an option, because mineral assemblages are important for, I mean, it surely tells us something about potential of ore formation, for say example, or concentration of certain elements in the fold hinge. But then understanding the kinematics should help the, the mineral assemblage in the fold hinge, the information regarding the mineral assemblage present in the fold hinge will only be assisted if we know prior to going to the chemical analysis, is that how the kinematics has evolved in that region. From that, actually, we can have a perspective on, so if this kind of intense deformation has happened to this area, then we can predict, okay, so based on the evolution of kinematic evolution of the fold, so what kind of materials can be precipitated in the fold hinge. That can be an estimation from the kinematic understanding. But then understanding the mineral assemblage alone will not actually help to understand what will be the kinematic evolution. Right? It's a other way around. So option B will, in this case, it will not be the best appropriate answer. It is definitely an appropriate answer, but it is not the best appropriate answer. Okay, so I may tell you. So option C is definitely the correct answer. And option A is also correct. And I will tell you why. Say, for example, I have a fold like this. And I have a fold like this. Right? So there are two folds. So now tell me which one is the symmetric fold and which one is the asymmetric fold.
The first one is symmetric.
Okay, so of course this one is symmetric and this one is asymmetric, right? Now for a symmetric fold, how the particles will flow, if I have to understand that the rotation and history of displacement of individual particles. So I can say that the forces were applied like this, and the movement of particles may have happened like, if this is my plane of symmetry, then from this side to this side, like, or the other way around, depending on the mechanism of folding. So then we can identify the path. And for this case also, if we know what is the distribution of the symmetry plane in this case, which is actually the axial plane of the fold, based on these we can say, So there is a sense of shear like this. And that's why particles have either, flown like this and like this. So the particle flow path can be reconstructed if we know how the axial plane is tilted, because based on the position of the axial plane, we can draw the flow path of the particles, how they have moved during progressive deformation. So that is why understanding the position of the axial plane is important for understanding the kinematics of the particles involved in a folding of a layer of rock. Because for understanding the kinematics or the kinematics or the motion of the particles, you always need a reference frame, right? Because you have to ultimately plot the thing in a 2D geometric coordinate or even in a 3D geometric coordinate. And what does a geometric coordinate means? It means actually a reference frame. So in reality, from a field observation, if you want to reconstruct the flow path of particles that are involved during the folding of a layer of rock, you do need some references. And the only thing that you can create for a symmetric reference point is the axial plane of the fold. That is why the dip and strike, or as we say, attitude of the axial plane, has to be known in order to actually measure how the particles have been flowing. And you can reconstruct the displacement path and the rotation history of particles during the development of the fold. So that is why option A and option C both will be contributed towards the kinematic model of the fold. Whereas option B will help us to understand the mechanics, the mechanistic aspect of the fold, because the mineral assemblage will tell us about the strength of the rock, and once we know the strength of the rock, then only we can understand how the stress has been applied or the other things that involves the mechanics. So understanding mineral assemblage that is present in the fold hinge line is a part that goes to the understanding of the mechanics of the folding, because it ultimately tells about the strength of the material. But option A alone is definitely a geometric aspect. Option B alone is definitely it has a contribution to the mechanical understanding. Option C is definitely a kinematic framework, but then in order to fulfill the proper kinematic model, you need some reference point. Then option A will serve that as a reference point. But then why not option D? Because whether a fold is upright or overturned does not influence the measurement of the displacement path of the particles. To draw the displacement path of a particle, you doesn't need to know whether the fold is upright or overturned or neutral fold. What is important to understand in this case has to be a reference frame. So option D does not provide you a reference frame, but option A does provide you a reference frame, that is the axial plane. And that is why option A is more important to being a contribution to the kinematic model than option D. So that is why option A and option C are the correct answers. Okay. Okay, so let us move on to the next question. We only have 4 questions left, so I think we can wrap it up early. Okay, option 7 says the mechanical model in structural geology primarily aims to, option A, catalog the different structural events observed in the field. Option B, relate the stresses and geological properties of rocks to the resulting strain and structural style. Option C, describe only the final geometry of a structure without reference to stress. Option D, replace the need for field mapping entirely. Option D, as you know, it is completely meaningless in this case. And probably the best observation in this case will be the best option in this case will be option B. Of course, it is the only correct answer, because mechanics involved understanding the stresses and the rheological properties of rocks that resulting in strain and structural style. Some rheology will produce brittle deformation, some rheology will of course produce ductile deformation, and whether the deformation is mm, brittle or ductile will depend on the amount of strain, amount of stress, and the strain rate. So in the coming weeks of, I mean, of this lecture series, we will definitely talk about the rheological aspects. It is very interesting thing, and I hope that you will find more interest on understanding how different rheological models are being applied. And I definitely will get a chance to talk about what is viscosity. I can tell you that is a very interesting thing, and understanding viscosity depends on understanding how you interpret strain rate. And I am sure that none of us can actually have a full picture how slow the processes are. I mean, how fast or how slow we can actually perceive. Geological strain rates are very, 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 very slow. Then how much slow is the slowest? That is the question. And how do we define viscosity, and why viscosity is important for understanding the ductile deformation processes, and how viscosity also contributes to understanding brittle deformation? It's a very important aspect. So we will talk on these matters more when we in the coming weeks, when we will go dealing with the ductile deformation, shear zones, and deformation mechanisms, rheological models, all these kind of things. So we will slowly learn in the coming weeks. Okay, so mechanical models in structural geology primarily aims to relate the stresses and rheological properties of rocks to the resulting strain and structural style. Simple. Okay, numerical and analytical models are especially useful in structural geology because they allow direct field observation of ancient deformation events, quantitative simulation of deformation patterns under specified boundary and rheological conditions testable against natural samples, complete elimination of uncertainty from geological interpretation, and determination of absolute age of rock. So what do you think will be the correct option in this case?
Should option B.
Yeah. So quantitative simulation of deformation patterns. So in next upcoming lectures, I may be able to show you some of the cool numerical simulations that has produced folding, faulting, and this kind of thing. So actually, computer simulations using numerical simulations using finite element methods is a very interesting tool that can actually tell us about how rocks behave if rocks are being treated as a different material, I mean a class of material, then which properties of the rocks can be used to actually replicate these kind of structures that we generally observe in the field in a computer, specifically in using the mathematical models, how can actually create that geometry. And also option C is partially correct, because once you get to replicate whatever you have got, whatever structures you're observing in the nature, you're just assuming this has happened. But then if you can replicate the same structure using some mathematical equations to replicate the geometry of the structures, then you are 100% sure that this is one of the dominant mechanisms through which this structure has formed. So numerical models are especially useful because it eliminates certain uncertainty from geological interpretation alone, right? So we geologists we just have the tool to observe and logically connect one thing to another, and then we interpret what is the best possible explanation for the structures we're observing, because nature is too complex. You just can't explain nature using just one single equation. It's very much complicated than that. But then we can apply some simplified mathematical model to replicate the simplest form that we are observing in the nature. The fold that we are producing through computer simulations might not be that intricate or complex that we observe in a field, but overall structure is being replicated using computer simulations, numerical analysis, something like that, finite element simulations. But then we have a chance to say that even though this model is very simple, it still can explain whatever structures we are getting, because we are getting a similarity in the geometry that is being independently produced through just mathematical equations and something we are actually observing in the nature. So there is a mathematical reasoning behind whatever we are observing in the nature, and that's why numerical and analytical models are useful in structural geology, because then we will not just only be able to understand things, we can also predict things, right? So why numerical simulations are important, I can tell you, is that because only the numerical simulations give us some mathematical equations that describe the structure, and now you have a mathematical equation. So what do you do when we have a mathematical equation? We can simply plug in some values to get y from x. And what is that? That is prediction, right? So if there is some values of x, we can say that this will be the possible value of y. And that thing is only applied to oil and gas industry, because they interpret the subsurface structure using geophysical data, they extrapolate the data and they analyze through numerical simulations, they get equations, and then they use that equation to derive how much amount of oil can be present in this location if this structure is present there, and they calculate some value, they get a value that is the prediction, and based on the prediction they drill holes and extract the oil or gas or coal or whatever natural resources we are talking about. So geological interpretation is incomplete because of this inavailability of the complexity of the structures. And then if we introduce some simple mathematical models, then we get a simple equation that can help us to not only just understand, but also to predict what the rock gives us, right? So that's why option B and option C both are, correct. Okay, this is a numerical exercise. A rock unit is buried to a depth of 8 kilometers beneath a sedimentary basin. Assuming an average overburden density of 2500 kilogram per meter cube and acceleration due to gravity is 9.8 meter per second square, calculate the approximate lithostatic or confining pressure at that depth, that is given at 8 kilometers, right? What will be the lithostatic pressure at a depth of 8 kilometers? So one thing I can say is that every time you just calculate, make sure you get units in the same system, whether it is CGS or SI. Check for that, convert into a same system, like convert everything into CGS or convert everything to SI, and then start putting into the formula, because otherwise you will mess up the decimal places and the value will come incorrect, right? So in case if you just observe the values here, it is megapascal, gigapascal, and these are the options given. So what is megapascal? That is 10 to the power 6 Pascal. And what is Pascal? Pascal is Newton per meter square. That means this is an SI unit, right? So if this had been CGS, it would be dyne per centimeter square. But we are not, the options are not given in dyne per centimeter square. That means it is a SI unit. So gigapascal is 10 to the power 9 Pascal, and megapascal is 10 to the power 6 Pascal. So then you know you need to apply SI unit. You have to calculate all the things into SI unit to get the correct options, right? So what will be the formula which we will applying here? So the formula is lithostatic pressure P is equal to H rho G. H is 8,000 meters because it is in kilometers. Rho is already given 2500, and then G is 9.8. So then you can calculate. So what will be the answer? Correct answer? The correct answer will be actually option B, 196 megapascal, right? Okay. So then we move on to the last question. So combining the concepts of scale dependence and homogeneity or heterogeneity, which of the following scenarios is most plausible? Option A, a rock mass that appears heterogeneous at outcrop scale may appear effectively homogeneous when viewed at a much larger scale, much larger regional scale, right? A rock mass that is homogeneous at one scale must remain homogeneous at every other scale. Option C, the scale of observation has no bearing on whether a rock behaves homogeneously or heterogeneously. And option D, heterogeneity can only ever be observed at microscopic scale. So what is the most possible answer?
Option A.
Exactly. And the opposite also correct. So homogeneous in small scale can also become heterogeneous in larger scale. Like that is which is in opposite to whatever there is in option D. Option D is saying that heterogeneity can only ever be observed at microscopic scale. That is entirely incorrect. Why? Because say for example, I am observing a banded iron formation. You all have heard about banded iron formation, BIF. So when you take a rock of BIF in the hand scale, is BIF homogeneous or heterogeneous? What do you think? So if I have a BIF rock, banded iron formation, or if I have a shale, laminated layers of shale, if I have a shale and if I have a gneiss, say for example, banded gneissic rock, and if I have a banded iron formation, these kind of rocks, these are layered rocks, right? So if I just look into the rock, what immediately comes to my mind? It is heterogeneous, of course, right? Because there are layers of different compositions. And if the composition is different, how come the deformation will be homogeneous? It has to be heterogeneous, right? So if I have a hand specimen rock that is BIF, and then I try to deform the rock, it of course the outcome of the deformation in the hand specimen scale will be of course heterogeneous, right? But then think again. If I select one particular layer, say for example the layer which has only chart and there is no iron ore formation inside, I'm just picking the chart layer and I'm zooming in and I'm seeing through the microscope. What I will see? I will see homogeneous deformation, because in that microscopic scale, I'm only observing one single composition, and in that one single composition, the deformation has to be homogeneous, right? Then it turns out when I'm zooming in, I'm actually changing from heterogeneous to homogeneous deformation. It is not always right that heterogeneity can only be ever observed at the microscopic scale. On the contrary, homogeneity can also be observed in the microscopic scale. So it has no relation on the, it has no relation with whatever in the scale of observation. The scenery can change depending on the scale of observation. Anything can become homogeneous at one scale, can become heterogeneous in another scale. Okay, so that's it. That's for week 10. So sorry, I'm sorry, it's for week 1. This was the last question. And then I guess this will be for today, and we will meet again on the next week. I do insist, please join on the next week, because we will do some numerical calculations on the deep and strike measurements of different numerical aspects of and numerical problems. Okay. So I'm stopping the presentation now, and I hope that you will join again on the next week. Thank you. I am ending the meeting. Yeah, thank you.